Welcome to the second part of the first lecture of ELE 311T. Uh, as we saw in the first part, we are basically trying to find out the complete time domain behavior of a network when it is subjected to an excitation. So we are not only interested in finding the steady state behavior, we are also interested in finding the transient behavior. Now the excitation that we generally focus uh, in this part is the DC excitation, because we have already seen the steady state behavior of a network when the excitation is DC in our first semester. So today in these lectures we're going to see the complete time domain response, steady state plus transient, when the excitation is most of the times DC. So one or two things related to DC circuits that we're going to see today. We're going to see first what is the steady state behavior of inductance and capacitor under DC excitation. You may be already knowing this, but we'll still revise it. So we know that for the inductor, the governing equation is this. So when the system has come to its steady state and the excitation is DC, it means that every variable has settled down. So you don't expect a rate of change in the current. Current would have reached a steady state value, some particular value, a constant value, because the source is DC. And normally, most of the times, you'd expect that di by dt under steady state conditions, in a DC circuit would be zero, because that's what steady state means. Loosely, it means that variables have settled down, and in DC, expect the variables to settle down to constant values. So this actually means that the voltage across the inductor will be zero, and that's why we say that the inductor acts as a short circuit in steady state, and this is with respect to DC circuits, not with respect to circuits which have other sources of excitation. Similarly, for the capacitor, we have seen that the current in the capacitor is given by this differential equation. Again, if the variables have settled down, the excitation is DC, the conditions are steady state, you expect dV by dt to be zero. You don't expect any rate of change in the variables, so you expect the current in the capacitor to be zero, and that's why we say that the capacitor acts as an open circuit in steady state. So these two things we have to remember. We have to, because we'll need this to solve the circuits that we're talking about. So now let us start and take an example and see how we can use our knowledge, whatever we have learned till now, to actually solve some problems. So our approach is going to remain the same. We are going to write down the differential equation for the circuit, and then we are going to see the initial conditions. So we write down the ODE, then we see the initial conditions, and we try to evaluate the conditions at 0 plus, assuming 0 to be the time of switching, and then we solve the ordinary differential equation. So let us take the circuit that we have done before. We are having say a DC source. It's connected through a switch to a resistor and an inductor. The switch closes at t is equal to 0. This is the voltage source. So suppose we want to find out the current, the initial conditions for the current, where this is the current flowing in the circuit at 0 plus. And we also want to find out the derivative of the current at 0 plus. This is just for our interest. We want to see whether we can obtain this information from whatever we have been told. We have been given the circuit, and we have also been told that the current at 0 minus is 0. So from our knowledge of the inductor, we know that since the source V is a constant DC source, it does not contain impulses. Impulses or the derivatives are absent. So inductor current has to be continuous, because any discontinuity in the inductor current would imply that the applied voltage has something that goes up to infinity. So inductor current is continuous means that I0 plus is going to be equal to I0 minus is going to equal to 0. So this is one of the two initial conditions that we have found. Now let us write the differential equation once the switch is closed. So once the switch is closed, this is closed. The differential equation that we get is simple. V is equal to Ri plus L di by dt. Now let us see what is this differential equation at 0 plus. At t is equal to 0 plus, because this equation is valid after switching. This equation is valid after switching, and that means that it is valid for all t greater than 0, including t is equal to 0 plus. So at 0 plus, what is the equation going to be like? It's going to be V is equal to R I 0 plus L. Let me write this as I dash 0 plus, the first derivative of current. We have already seen that I0 plus is 0 here. So that means we can write I dash 0 plus is V by N. So our knowledge of this circuit behavior, our knowledge of the inductor characteristics helps us in finding both the initial conditions, the current at 0 plus and its first order derivative at 0 plus. So this information is later used to actually write the complete solution for the circuit. Similarly, the information that at steady state in DC circuits, the current through the capacitor has to be 0 and the voltage across the inductor has to be 0, can be used to write down solutions for various problems. Like for example, this is the network that has been given to us. There is a switch here. We are told that the network has reached steady state before the switch moves from A to B. So the switch is initially connected at A and it then moves to B. But it has been connected to A for a long time, and after being connected to A for a long time, it moves to B. We are asked to find the initial conditions for ILT and VCT and their derivatives, and we are also to find the final values for ILT and VCT. So let us assume that this switching that has taken place, let us assume that 0 is the instant of switching. 0 is the switching instant. So at t less than 0, the circuit conditions are something like this. When the switch is connected to A to B, so the conditions are something like this. The inductor is there, the capacitor is there, the resistor is there, and the switch's network has reached steady state before the switch moves from A to B. So you have 5 volts source connected, and then at t greater than 0, the switch has moved to B, so you have now a 10 volt source connected. So a 10 volt source connected. And what we are asked to find is initial conditions for ILT and VCT. Please remember that the initial conditions mean the conditions just after switching always. So initial conditions that we need to find are for IL. What is IL at 0 plus? What is VC at 0 plus? And also what is IL at dash at 0 plus, because we are asked to find the derivatives also. And what is VC dash at 0 plus? And we are also asked to find the final values. So we are asked to find IL at infinity and VC at infinity. So these are the quantities that we are interested in. Now let us see what we can do, how our knowledge of the inductor and capacitor behavior can help us in trying to find solution to this problem. So let us come to this circuit, which is the condition of the circuit at t less than 0. So this is the state of the circuit for a long time up to 0 minus, and So we can simply say that the circuit would have achieved a steady state. That means this voltage across this inductor would behave like a short circuit. The capacitor would behave like an open circuit. So actually there's going to be no current through the capacitor and no voltage across the inductor. In that case, what is left is just the source and the resistor. If this is an open circuit and this is a short circuit. So if you see that condition, if you visualize that condition, you'll see that since this is a 1 ohm resistance, the current is going to be 5 amperes, and all this voltage drop is going to happen across the resistor, which in turn means that the capacitor would also be at 5 volts. So we can simply write, by our insight regarding the steady state behavior of the inductor and the capacitor, the steady state behavior of the inductor and the capacitor in DC circuits, we can write with that insight that for this circuit IL 0 minus is going to be 5 amperes and VC 0 minus is going to be 5 volts, because the circuit has reduced to just a source in series with a resistance. Now this information we are going to take across to this circuit here, and we know that since the source is a DC source, it does not contain impulses. The value of the current at 0 plus is going to be equal to the value of the current at 0 minus. It's going to be equal to 5 amperes. The value of the voltage at 0 plus is going to be equal to the value of the voltage at 0 minus. It's going to be 5 volts. Now let us come to finding so we have found two of the quantities that we are interested in. Now let us come to finding the derivatives of the current and voltages. So I'll wrap this circuit because we are not interested in this any longer. We have taken out all the information that we wanted. So let me wrap this also. Now let us write the differential equation for this circuit. Please remember that this is ILT. This voltage is VCT, and this current we can label for the time being as IRT. So if you write the differential equation for this part of the circuit, you can write that minus 10 plus L DIL T by dt plus VCT going to be 0. And since the inductor is 1 Henry, we can write this minus 10 plus IL dash T plus VCT is equal to 0. At T is equal to 0 plus, and this equation is valid for 0 plus because this circuit is valid for T greater than 0. We can write this equation as minus 10 plus IL dash 0 plus plus VC 0 plus equal to 0, and this simply gives us the value of IL dash 0 plus. IL dash 0 plus is going to be minus VC 0 plus plus 10, which is VC 0 plus is already known, 5 minus 5 plus 10, that is 5. So this is 5 ampere. Remember, this is IL dash 0 plus, so it's ampere per second. So this is another variable that we have found. Now we need VC dash 0 plus, and for finding VC dash 0 plus we can use the second part of the circuit that we have here. So you can write, if we see this node here, we can it's clear that ILT is C dVc t by dt. Remember, we need VC dash 0 plus, so we need to put this somewhere in the equation, and we can do that by writing the nodal equation for this node. ILT is equal to C dVc t by dt plus IRT if you apply KCL at this node. So you can write this ILT as C is 1 farad, so we can write this as VC dash t plus IRT. Now IRT is this voltage divided by the resistance that is here. So ILT is going to be VC dash t plus VCT by R. And writing this for the 0 plus t is equal to 0 plus instant, we can write IL 0 plus is equal to VC dash 0 plus VC 0 plus, and R is 1 ohms. So this gives us VC dash 0 plus is equal to IL 0 plus minus VC 0 plus. So IL 0 plus is 5, VC 0 plus is 5. This is 0 volts per second. So this is another quantity that we wanted. We wanted the derivative of the capacitor voltage. So you see, we have obtained the initial conditions at 0 plus and the values of the derivatives at 0 plus using our insight into the inductor and capacitor characteristics and our insight and the knowledge of the differential equation governing the circuit. So these four quantities were the ones that we were interested in. Now the next thing is to find IL at infinity and VC at infinity, which is very simple because we know that at infinity this is going to behave like a short circuit, this is going to behave like an open circuit. So you just have a source in series with a resistance which is 1 ohms. So at infinity this IL is going to be 10 divided by 1, that is 10 amperes, and this VC is going to have all this voltage in parallel applied across. So VC is going to be 10 ohms. So the problem is solved. We know the circuit variables and their behavior at 0 plus, 0 minus, and infinity. Seen that we can find the initial conditions of the variables of the system, and we can find the final conditions of the variables of the system by using our insight into the behavior of the inductor and the capacitor, and by writing the differential equations for the circuit. Now let us extend the problem slightly. Let us assume that we want to find out ILT and VCT as functions of time for the circuit. That is to say, we want to completely determine the time domain response of the circuit as the circuit switches from A to B, wherein it has been connected to A for a long time. So in this case, for all the information related to the circuit behavior when it was connected to A, has been obtained, and it is here. So we need to analyze the circuit for t greater than 0, that is when it is connected to B, and then find ILT and VCT as required. So for t greater than 0, we can write down the circuit like this. It will be the circuit condition would be something like this. And then we need to write down the differential equations and use these initial conditions to find out the final solution for the circuit. So since we are asked to find ILT and VCT, we'll write down the equations in terms of these two variables only. Although you could use other methods here like mesh analysis or nodal analysis, but let us do it by writing the two equations corresponding to the two parts of the circuit in terms of ILT and VCT. We have done this before, but still, for the first part of the circuit here, the first mesh, we can write minus 10 plus IL dash T, which is LdIL by dt, plus VCT equal to 0. So this gives us the first differential equation, VCT plus IL dash T equal to 10. And for the second mesh of the circuit, we can write down IRT into R, which is 1 ohms, minus VCT equal to 0. And IRT, since it is not a variable in which we are interested, we can write down IRT as ILT minus ICT, the current flowing in the capacitor, and ICT is C dVCT by dt. So we can write down, let us say for 2 minutes, ICT minus VCT equal to 0. So we can write for the second part ILT minus, instead of ICT we'll write VC dash T minus VCT equal to 0. So this gives us the second mesh equation, which is VCT plus VC dash T minus ILT equal to 0. So these are the two equations. So what we have is a set of simultaneous differential equations in terms of the variables VC and IL. So now let us solve these simultaneous differential equations. So we can write both of them together in matrix form like this. So this is going to be the first equation. This is going to be 1 P. The second equation is P plus 1 minus 1, where P is the differential operator, VCT ILT is equal to 0. So this is no, sorry, not 0, is equal to 10 0. So we have done two things as far as the circuit is concerned. We have taken all the information in terms of initial condition and we have written it down. We have written down the differential equation for the circuit. Now the third part is solving the differential equations and using this information to find out the final time domain behavior of the circuit. Now this is something that we have already done using our knowledge of differential equations, but let us do it here again. So this is a non-homogeneous system of equations. It has a forcing function which is non-zero. So the solution would be the sum of the complementary function and the particular integral. The complementary function is the solution of the homogeneous counterpart of this set of equations, which can be obtained by writing the characteristic equation and finding the values of P. So the characteristic equation for this circuit would be 1P, the determinant, equal to 0, which is minus 1 plus p, sorry, minus 1 minus p plus 1 equal to 0. This is p square plus p plus 1 equal to 0. And this is basically complex. P is minus half plus minus root 3 by 2j. So the complementary function part, which is part of the solution, we can write this as star if you want, is going to be m1 e to the power minus half t sine root 3 by 2 t plus phi 1, where m1 and phi 1 are to be determined, and ILT again star, because this is only part of the solution, it's the complementary function only, is going to be m2 e to the power minus half t sine root 3 by 2t plus phi 2. Now this is the complementary function part. What is the particular integral? The particular integral is obtained by looking at the forcing function and by substituting appropriate appropriate values of the variables which uh, are similar to the forcing function. So from the forcing function, as we see it, the forcing function is a constant, so the particular integral is also going to be a constant. So the particular integral part, if we write it as hash, is going to be a constant. ILT is going to be a constant b. Now we can find out the values of a and b by substituting back in the differential equation, because the particular integral is a solution of the differential equation, and it is a solution which exists alone irrespective of the complementary function. So when we do that, when you put this in the first differential equation, you'll get this value of VCT and this value of ILT. You'll get in the first differential equation, you'll get A plus differential of B, which is 0, is equal to 10. So the value of A is 10. And in the second differential equation, you have differential of A, which is 0, then A, and then minus B. So A minus B is 0. So B is equal to A. So A is equal to B is equal to 10. This is the particular integral. And if you see that this is something that stays, as we have already discussed this before, this is something that stays. This is the forced response of the circuit, and the complementary function is a natural response of the circuit. This can also be obtained by looking at the circuit and finding the values of steady state values of the two variables that we are interested in, which we have already done, and we have already seen that the steady state values are going to be 10 for both IL and VC, and that is what we obtain here also. The particular integral is going to be 10. So you can find out the particular integral by analyzing the differential equation, or you can also find out the particular integral in terms of circuits by looking at the circuit and trying to see what are the values of the variables that are going to remain after a long time. That is the particular integral. So in any case, the final value for VC and the final value for IL is the sum of the particular integral and the complementary function, which in this case is uh, plus 10 and plus 10. So we'll rub this star off. So this is the value. These are the values of the capacitor voltage and the inductor current. Now we have to find M1 and phi 1. M2 and phi 2. This information is obtained by substituting for the initial conditions. I can wrap this off. So now let us substitute the initial conditions. So what is VC0 plus? VC0 plus is 5, and if you substitute 0 here on the right hand side, you'll get M1 sine phi 1 plus 10. So this gives us M1 sine phi 1 as minus 5. Then we have VC dash 0 plus, which is 0. So we have to differentiate the first equation. So this is going to be M1 e to the power minus half t sine, differential of sine is cos root 3 by 2t plus phi 1 into root 3 by 2 plus M1 sine root 3 by 2 plus phi 1 into e to the power minus half t into minus half, and this thing has to be evaluated at t is equal to 0. This is 0 plus, and this will be equal to 0. So this gives us the second equation, M1, putting t is equal to 0, cos root 3 by 2t multiplied by root 3 by 2 minus half M1 sine root 3 by 2t. This is plus phi 1. This is plus phi 1 equal to 0. Again, t has to be put in 0. So this is root 3 by 2 M1 cos phi minus M1 by 2 sine phi 1 equal to 0. So this gives us, taking this on the right hand side and dividing by tan, you get tan phi 1 is equal to root 3. So phi 1 is tan inverse root 3, and from this and this you get M1 is equal to minus phi by sine phi 1. So tan inverse root 3, that is phi 1 is 60 degrees, and M1 is minus 5 by sine 60 degrees, that is minus 5 into 2 by root 3, that is minus 10 by root 3. So we can write down VCT as minus 10 by root 3 e to the power minus half t sine root 3 by 2t plus 60 degrees plus 10. Similarly, by using the initial conditions for ILT, IL dash 0 plus and IL 0 plus, we can find the values of M2 and phi 2. So in this problem, we learned a couple of things. We learned how to find the initial conditions and how to use them to solve the differential equation for the circuit. And we learned how to find the particular integral of the circuit by looking at the steady state values and by applying the properties of inductor and capacitor at steady state in DC circuits as we know.